Hello folks, this is the second part of relative max, relative min, relative extrema, increasing, decreasing intervals of functions examples. So I'll continue with this second part. So we said a critical number was a number at which the derivative is zero if, or it doesn't exist. Now let's say we have a function of this type. Again, you need to find the derivative f prime of x. For this type of functions, you see you have an exponential and you have a polynomial. So you need to use the product rule, the first function and the second function. The derivative of the first function is 2x times the second function e to the negative x, plus I keep the first function the same, x squared, and the derivative of second function is e to the negative x times the derivative of the exponent, which is -1. So this is the product rule. So I use a product rule in this example. Product rule: if you take the derivative of a product, that's the derivative of first times second plus first times the derivative of the second. Now from here, you need to simplify. I have 2x here, I have x squared in here, and I have -1 in here because I have both e to the x squared occurs in this both terms. So we have 2x minus x squared times e to the negative x, and I set that equal to 0. Now, any exponential function with any positive, of course, like the bases are positive, so this exponential expression will be positive. So I need to set this side equal to 0, and you can factor that easily. Say it's a binomial quadratic equation, quadratic expression. So I can take x out and I'll have 2 minus x. Set that equal to 0, so we got x equals 0 or x equals to 2. So these are the critical numbers for this function. Now let's check the sign of f prime now. So we will do the table. We can do the table. Let's do it here. Do the table. Here's negative infinity. Here's infinity. Here I have 0. Here I have 2, and I can pick up some testing values from here. I can take -1 from here, 1 from here, and 3 from here. So if you look at, like, you don't, this part is f prime, yes, that's right, which is simply 2x minus x squared times e to the negative x. But keep that in your mind, this e to the negative x is always positive, and positive numbers, there's no effect on the sign because plus times minus is minus, plus times plus is plus. So you only need to check the sign of this portion. So plug that testing value in here. So in the first one I have 2 times -1 and then minus -1 squared, and that will give me a negative number. It's going to be -3. So it's going to be -3, which is negative. If you plug in 1, it's 2 times 1 minus 1 squared. That's going to be positive. You check that one. And if you plug in 3, 2 times 3 minus 3 squared. So that's 6 minus 9, and that's going to be negative. So the signs are negative, and then positive, and then a negative. So our function here has a, first it decreases, and then it's increasing, and then it's decreasing. Here it has a relative max. Here it has a relative min. And we can write here the increasing intervals. The increasing intervals, it's just 1, it's 0, 2, and then the decreasing intervals though are negative infinity, 0, union 2, infinity. So that's the decreasing interval, and we need to find the value of the function at those points. So f of 0 is 0 squared times e to the negative 0, so that gives you 0. So we have the point 0, 0. And then f of 2 will be 2 squared times e to the negative 2. So that's 4 e to the negative 2. Or in other words, sometimes you can write it as 4 over e squared. So if you write down the max mins, So f has a relative max at, let's see, we write it down here, relative max at 2 comma 4 e to the negative 2, and then f has a relative min at 0 comma 0. So this is just another example in which a polynomial combined with an exponential function, and we find the increasing decreasing intervals, and we find the relative max and relative min. Now in the next example, actually this problem is just a rational function, but only relative max, relative min is asked in this problem. So we first need to find the derivative. So f prime of x. Now you need to use the quotient rule. For this one we have to use the quotient rule. Okay. So the derivative of top is 0 times whatever you have in the bottom. Doesn't change, that will make it 0. And then the bottom we got minus, the top is negative 8 times the derivative of the bottom, which is 2x. And the divide whole expression by x squared minus 1 squared. So that gives us 16x divided by x squared minus 1 squared. And if you set that equal to 0, you see there are numbers at which it's not defined, does not exist, but those numbers are out of the domain. So here we have to make sure that x can't be negative 1 or positive 1. So those are not in the domain. So that's why those are not critical numbers. The critical numbers are the ones in the domain that makes f prime 0 or undefined. So here we have only one critical number, 16x equals 0, which makes x equals to 0. So this is the only critical number. So if we have a maximum or minimum for this function, it should occur at 0. So let's check the sign. I mean, let me just write it down. 16x divided by x squared minus 1 squared is what we're checking. And folks, here, just to make it clear, just this is a squared. Don't forget. So that's going to be every time positive. Keep that in your mind. And if you mark here 0 and here infinity, here negative infinity, of course there are numbers at which it's not defined, but we don't have to check that because we're only checking the relative extrema. Don't forget, we're not checking the increasing decreasing intervals for this problem. So before 0, you see if you plug in something less than 0, like now let's take like negative 1 and 1. If you plug in negative 1, that's going to be negative, obviously, because 16x. And if it's 1, that's going to be positive. So it's decreasing before 0 and increasing after 0. So at 0, we have a relative min for this function. So this is how you find the relative extrema. And if you plug in 0 in your function, it's going to be negative 8 divided by 0 squared minus 1. So it's going to be positive 8. So this function has a relative min at 0, 8. This is how you find the relative extreme only. Increasing, decreasing intervals, it's not covered for this problem. Okay, this is another example with the rational functions. We have one more example. Here's our last example, and it's an application problem. The temperature of a sick person is given in here. So you will realize that this is I just want to emphasize something in these problems. When you see negative some coefficient times t squared, that you know that it's a quadratic. Of course, these are going in a descending order. And we know how the quadratics really behave as a graph. It's a negative leading coefficient, so it opens down. So you expect a maximum for this function at the vertex. So, and this maximum occurs when the derivative is 0. It's really that simple. So it starts actually at 0 and then it goes up to 16, so it just lost 16 days. But the problem asks us to find the maximum temperature of this person through this period. So it's straightforward. You're looking at the relative max. It's a beautiful problem of applications of relative extrema. So you find the derivative of t, and that's going to be negative 0.2 times t plus 1.6 equals 0. And if you solve that, negative 0.2 times t equals negative 1.6. So if you divide both sides by negative 0.2, you will get t equals 8. So in 8 days, this guy will hit the maximum temperature. This is when t equals 8 days, after 8 days. So how can we see that algebraically though? Like, I mean, how can we see this? How can we see this algebraically? It's simple. You will do the same thing. Let's just check the sign. So here we have 8. Max we have 16. Min we have 0. It's between 0 and 16. And this is t prime. So it's negative 0.2 times t plus 1.6. So like, take two different values. Let me just use a different color. Two different testing values. Take, for example, 7 from here and take 9 from here. And you can see, if you look at t prime of 7, okay, it's going to be negative 1.4 plus 1.6, so it's going to be positive. You can check that. If you look at t prime of 9, if you plug in 9, that's going to be negative 0.8, negative 1.8 plus 1.6, it's going to be negative. So it's like increasing and then decreasing. It's plus here and then minus here. See, it's exactly what we expected. But we see that algebraically. So we have a relative max here. When actually, if you want to write down the increasing intervals, you can just say increasing interval is just 0, 8, because it starts at 0. And then the decreasing interval is 8, 16. So that shows the increasing, decreasing intervals, and we have a max here. We call it the first derivative test. So what you do is now you need to find the value at there. So t of 8 is what you need, and if you plug this in there by using a calculator into the original function, just keep that in your mind. You will be plugging into this one. You will be using the actual function. The value that I got is 105.2. So this is the maximum temperature. So it's kind of like this relative max for this function at the point 8, 105.2. So see, this guy hit the maximum on day 8 and then started to go down and went back to the normal at the day 16. So that's a good application problem, but really, I mean, if you have a good graphing calculator, you can visualize all these algebraic progress solutions on your graph as well. So I hope this video will be helpful as well. See you next time. Bye.